In this video, we're going to talk about the chemistry of the carbon-carbon triple bond, otherwise known as the alkyne. We're going to cover topics such as the physical properties of alkynes, naming of alkynes, their remarkable acidity, especially if they have a CH bond on the end of the alkyne, ways that we can exploit that acidity to synthesize new alkynes, and then reactions that alkynes undergo. What you're going to see is, by and large, the chemistry of alkynes is going to be virtually identical to the chemistry of alkenes. Reductions of alkynes and other reactions of alkynes occur by addition, whereas most of the ways to synthesize alkynes are by elimination, just like we've seen for alkenes. Okay. So just to refresh your memory, recall that if you have a triple bond, that's going to be composed of a single sigma bond and two pi bonds. The sigma bond is here between the two carbon-carbon bonds. You have a p orbital and a p orbital that are overlapping side to side, which is one pi bond, and then you have another p orbital perpendicular to that, which is overlapping side to side, which is your second pi bond. Pi bonds are weaker than sigma bonds, so we're going to see most of the addition reactions are going to take place via donation of electrons from one of those pi bonds. I like to think of alkynes as corn dogs, where the carbon-carbon sigma bond is the delicious hot dog in the middle of the corn dog, and then there is a cloud of electrons, which is almost cylindrical, that's surrounding that carbon-carbon bond, where you have a p orbital sort of in this direction, a p orbital in this direction, but because of the size of the p orbital, what you end up with is just kind of a hazy cloud of electrons. All right, so what do you want to remember about alkynes? Well, they have a very, very strong carbon-carbon bond because it is a triple bond, but remember that to break one of those bonds is relatively easy because pi bonds are relatively weak. The carbon-carbon bond is the alkyne is the shortest carbon-carbon bond because triple bonds are shorter than double bonds. And remember that since these carbons are sp hybridized, the angle here is 180 degrees and the angle here is 180 degrees, so that would be a linear geometry. When you burn it, you release a lot of energy because it's a strong bond. And just like alkenes, this di-substituted alkene is going to be more stable than a mono-substituted alkene, so this is more stable. Same thing goes for alkynes, so this is called an internal alkyne, and that's going to be more stable than your terminal alkyne because it's more substituted. The most important thing is that if you have a terminal alkyne, it's going to have a CH bond on the end, and that is extremely acidic, much more so than any CH bond in an alkene or an alkane. All right. So how do we name alkynes? Well, generally speaking, I want you to be familiar with these common names. A 2-carbon alkane we know is ethane. A 2-carbon alkene, the common name for that is ethylene. The IUPAC name would be ethene. Remember, we drop the ane suffix and we add an ene suffix. So the IUPAC name for a 2-carbon alkyne would be ethyne. We add a yne suffix as opposed to an ane suffix. The other thing to pay attention to here is how the acidity of this CH bond changes as the hybridization changes. In an sp3 CH bond, it is not acidic at all. In an sp2 CH bond, the acidity increases slightly, but notice that the acidity really jumps up there. pKa of 25 means that this is 20 orders of magnitude more acidic than an sp2 hybridized CH bond. So we have bases that are capable of deprotonating these hydrogens that have a pKa of 25. Before we talk about that, I want to talk about a more systematic way of naming alkynes. Once you get beyond 3 carbons, then you need to specify where the alkyne is with the number. We're familiar with this. So we can call this 1-pentyne because the carbon-carbon triple bond is the first bond in the molecule, whereas since this is the second carbon-carbon bond, that's 2-pentyne. It's also acceptable to name this as pent-1-ine or pent-2-ine. Okay, so the first way we're going to talk about to synthesize alkynes is to exploit this idea that you can deprotonate this CH bond. The base that we're going to use to deprotonate this is called the amide anion, which is the conjugate base of ammonia. So the NH2 minus anion can deprotonate this hydrogen. Those electrons are going to go onto the carbon. And notice this is a negatively charged carbon, so it's a really good nucleophile. This is referred to as the acetylide anion. Now we can use this nucleophile to do chemistry, such as SN2 reactions, as we're going to see on the next slide. The reason why this works, remember, is that the pKa of ammonia is 38. So this CH bond is actually more acidic than this CH bond. So you're going from a stronger acid to a weaker acid. You're going from a stronger base to a weaker base. The equilibrium is going to move in this direction and favor formation of this carb anion. How can we exploit that to do chemistry? Well, what we can do is take a terminal alkyne. This has 5 carbons in it, 1, 2, 3, 4, 5. We can deprotonate it with sodium amide to get a carbanion, which is going to look like this. This, remember, we said is a good nucleophile. So if we want it to undergo SN2 reaction, we'll add a non-hindered electrophile like this iodide. SN2 reaction will happen where we'll get a new carbon-carbon bond between these two carbons, and now we have a new 7-carbon alkyne. We went from a terminal alkyne to an internal alkyne using this strategy. So this only works if you have a terminal alkyne. If you wanted to make some new molecule with this internal alkyne, you would kind of be stuck because there's no acidic hydrogens on that guy anymore. So how do we make other alkynes? Well, recall that the way that we made alkenes was to produce one new pi bond by an E2 reaction with a strong base. Let's say we take this compound and react it with sodium hydroxide. Hydroxide is going to accept this proton. These electrons are going to become your new pi bond. The bromide leaves, and we've eliminated HBr effectively to get one new pi bond. So if we want to make an alkyne, what we're going to do is 2 E2 reactions. So what we need is 2 leaving groups. We have 2 bromides on this molecule, and since they're on the same carbon, we're going to call this a vicinal dibromide. So if we react a vicinal dibromide with a strong base like sodium hydroxide, sodium methoxide, sodium ethoxide, 1 E2 reaction occurs to make an alkene. Second E2 reaction happens to make the alkyne. The mechanism is the same as the E2 reaction that we've seen in the past. So what kind of reactions do these alkynes undergo? They undergo addition reactions primarily. And one of the things that we talked about in the alkene chapter is addition of hydrogen. So if we hydrogenate this alkene in the presence of a platinum catalyst, we get 2 new hydrogens, 2 new sigma bonds, and we get an alkane out. Same thing happens when we hydrogenate an alkyne in the presence of a platinum catalyst. First we add 2 hydrogens across to get an alkene. Remember, that's a syn addition, but since the alkenes can undergo hydrogenation under the same conditions, what we end up with is an alkane. So hydrogenation of an alkyne with platinum and hydrogen gives you alkanes. Hydrogen adds twice, H2 adds twice, you get 4 new CH bonds there. Okay, but let's say we wanted this guy. Let's say we wanted to stop at the alkene. What we would do is add a poison or create a less reactive catalyst. Because what happens to be the case is that the carbon-carbon pi bond in the alkyne is the weakest. So that's the most reactive. So if we poison the catalyst, it's reactive enough to stop at the alkene and will not undergo further reaction. And the name of that poison catalyst is called Lindlar's catalyst. So if we hydrogenate an alkyne with Lindlar's catalyst, what we find is that we make the cis alkene only. And that makes sense because remember, hydrogenation is a syn addition. So the two hydrogens are going to add to the same side of the alkene to get a cis alkene. So that happens, hydrogenation with Lindlar's catalyst, which is a poisoned catalyst, produces the cis alkene only and stops. What if we want the trans alkene? Then what we want to use is a technique called dissolving metal. You use sodium metal, which remember has one valence electron. That electron gets donated into the pi bond, which then accepts a hydrogen from ammonia. I'm not going to go into the details of the mechanism, but it is in a textbook if you're interested. I'm also not going to ask you questions on the exam about it. But notice that the dissolving metal reduction ends up giving you a trans alkene. So you have options. You can make a cis alkene or a trans alkene from an alkyne, depending on the reagents that you choose to use. So to summarize here, if you want a cis alkene, you're going to use hydrogen and Lindlar's catalyst. If you want a trans alkene, you're going to use sodium and ammonia. If you want an alkane, you don't poison the catalyst and you just add hydrogen that way. Also recall that with a trans or a cis alkene, hydrogenation is just going to give you the alkane. Okay, so let's wrap it up here. Recall, alkynes are sp hybridized, which means that they have bond angles of 180 degrees and they are linear. They are named with a YNE suffix, and if you have an alkyne larger than 4 carbons or larger, then you need to specify where the triple bond is. The CH bond on the end of the alkyne can get deprotonated with sodium amide to give you a carbanion, which can do chemistry, namely the SN2 reaction, to make new alkynes. Double E2 can also give us alkynes from vicinal dihalides 2E2 reactions. We can synthesize alkynes from terminal alkynes via this chemistry that I just talked about, or we can reduce or hydrogenate alkynes. If we use Lindlar's catalyst, we get cis. If we use sodium and ammonia, we get trans.